Okay, cool. So we care about, so the two key resources that we care about are computation and the amount of data. And this what we've been talking about. In particular, we've been talking a lot about the sample complexity or confidence bounds or generalization guarantees question, which is related to the amount of data that we need for learning. And we've mentioned this a few times by now in order to even pose a question in the formal model to think about. And so the model that we've been talking about so far is a distributional learning model, which is actually what the PAC model of Valiant captures, and also the statistical learning theory framework of ABNI captures the exact same scenario. So in these frameworks, we assume that we have a distribution over the space of unlabeled samples. So for example, a distribution over the space of email messages if you want to do spam detection. And then we imagine that in the training phase, first a random sample of these examples is labeled by an expert. For instance, it's being spam or not spam for the spam detection problem. And this then is given as an input to a learning algorithm, which then outputs a hypothesis function that is then used to classify new subsequent examples that come from the same source as our training data. Okay? And obviously, right, so we care about getting classifiers with good generalization error. And the notion of error that we've been talking about is the zero-one loss or the classification error loss, which is defined just as the probability that our classifier predicts differently from the target function on an example that comes at random from the same underlying source. Okay, so I'm not going to go in detail through this slide because I assume that by now you guys are very familiar with it. I've been through it a couple of times already. Okay? So the one thing that I want to mention is that within this distributional learning scenario, the way we typically talk about a bias, an inductive bias, is by fixing a hypothesis space H, like linear separators or decision trees and so on, and then trying to compete with the best classifier in that hypothesis space H. Okay, so here the implicit assumption would be that we believe that there exists a classifier in our hypothesis space or in our class that is close to the target function. Okay, and we've been talking about two different cases. The first one is the realizable case. So this is the case where we assume that the target function truly belongs to the class. So this turns out to simplify the underlying I guess, math quite a bit, and still captures the essence of many of the key questions. Okay. However, the more realistic case is where the target function doesn't necessarily belong to the concept space, but it's close to some function in the concept space. And this is called the agnostic case. Okay, cool. And so we've seen in the last couple of lectures sample complexity result within this framework. So here we want to know how many samples we need to see in order to be confident that if we optimize over the training sample, we'll also do it in the future. And in the case where, in the realizable case, in the case where the target function truly belongs to my concept space, we've proven actually sample complexity statements for a very generic type of algorithm for a consistent learner, where essentially what we do, we just output a classifier that is consistent with all the data in the training set. So output a classifier that perfectly correctly classifies the training set. Okay, so this is a generic algorithm. It can be logistic regression or ID-free and so on. The only requirement that we have is that the classifier that we output perfectly labels the training data. Okay, and we have seen that for such consistent learner, we have very generic sample complexity statements, both in the case when H is finite and in the case when H is infinite. Okay, now in the case when H is finite, the number of samples that we needed depended only logarithmically in the size of H, okay, which is great, because it means we can handle hypothesis spaces that are very large and still learn with only a number of training samples. Okay, now in the case where H was not finite, obviously we could not use size of H, but we've seen last time that we can instead use a very nice combinatorial quantity called the VC dimension of the concept space that really kind of quantifies the effective dimension of our concept space. Okay? And so you get a similar sample complexity bound where basically we just replace log size of H with the VC dimension of H. And we also have an additional log 1 over epsilon factor, but we don't know if it truly should belong there or not. Okay, but in principle, we get very generic, very nice sample complexity statements. Okay, so do you guys remember what is the VC dimension of the concept space? We talked about it last time. It's not relevant for the lecture today, but still, I just want to quickly recap it. I mean, what's so nice about it is that it's easy to even describe in words, right? We don't need something very complicated. We don't even need to write down anything. So what is the Vista dimension of a concept space? So now, this is relevant for cases when the hypothesis space is infinite, right? Can you give me an example of an infinite hypothesis space? Linear classifiers, perfect, cool. So it's an example, or can be linear classifiers in RD, or decision surface of degree 2, and so on, right? Many examples. Most of the interesting examples of hypothesis spaces are infinite, right? And what is the VC dimension of the hypothesis space? Excellent. Okay, so Sweta is just right spot on. So the VC dimension of the concept space is just the cardinality of the largest set that we can shatter, we can label in all possible ways with concepts from our concept space. Okay, so that's the VC dimension of the concept space, and there are very nice generic sample complexity results that depend entirely on this combinatorial quantity, right? And last time, for example, we even computed the VC dimension for several concept spaces. And so just one example to keep in mind, for example, if we are thinking about linear separators, when the VC dimension of a linear separator in RD is D. Okay, so then we immediately get a sample complexity statement for algorithms that output linear separators. Okay, and just also to mention here, because this is important for the lecture today, so in the realizable case, where we truly believe that the target function belongs to the concept space, and the sample complexity is only linear in 1 over epsilon. Okay, and so again, this is a sample complexity statement that gives us confidence. Okay, so what this sample complexity statement here says, let me read this one. So if the number of training samples I see in the training phase is 1 over epsilon times the VC dimension of the concept space, times log 1 over epsilon plus log 1 over delta, then I can be confident that with high probability at least 1 minus delta, all the hypotheses of true error rate at least epsilon are inconsistent to the data, which then implies that I can be confident that with high probability at least 1 minus delta, all the hypotheses that perfectly label the data will have true error rate at most epsilon. Okay, and so for such statement, the sample complexity dependence on 1 over epsilon is only linear in 1 over epsilon. Linear in 1 over epsilon is linear in the VC dimension for the concept space when H is infinite, and only logarithmic in 1 over delta. Okay, but this is the realizable case, right? And this is just a slide mentioning, right? When, right? So this is a slide that mentions the example of linear separators. Okay, we can't read last time. Okay, so but this is for the realizable case, but the more interesting case from a practical point of view is the agnostic case, where the target function does not necessarily belong to the concept space. And I've already kind of mentioned how things get handled in that case, but I want to go through it a bit more slowly again today, because it's very important. So let's think about the case where the target function does not necessarily belong to our concept space. Let's call the agnostic case. Now, in that case, obviously, we cannot output a classifier. I mean, the algorithm might not be able to find a classifier that is consistent to the data. Obviously, there might be none. Okay, but instead what we can do, we can just try to find a classifier that has the smallest empirical error, right? Just find the classifier with the smallest error rate over the training sample and just output that. Yeah, that's called ERM, empirical risk minimization. It's a very natural algorithm, right? Okay. And now, turns out that actually can provide sample complexity statements for this type of algorithm that look very similar to the ones for the realizable case with a key difference. The sample complexity, you'll see, depends quadratically in 1 over epsilon instead of linearly in 1 over epsilon. So the terms look identical except for this 1 over epsilon squared dependence now in the agnostic case as opposed to the realizable case. Okay, so and in particular, what do I mean by sample complexity statements here? So now, the type of sample complexity statements that we're gonna think about are uniform convergence bound. So what we're gonna say is, if the number of training samples I see in the training phase is this quantity over here, 1 over epsilon squared times the VC dimension of the concept space plus 1 over delta, then with high probability, uniformly for all classifiers in my concept space, I have that their true error is within epsilon of their empirical error. Okay, so this is what we can prove in this case. So these are called uniform convergence results, right? And obviously, if we're able to guarantee this, right, if we're able to prove a statement of this form, then if I do empirical risk minimization, then, right, if I see so many samples and then I do empirical risk minimization, then what can I guarantee about the true error rate of the classifier that I output? Is moving to epsilon. Okay, good. So I mentioned it the other day. Let me also mention it again via picture, actually, right? So if I manage, here's the picture, right? So if I manage to prove that basically, right, so if I see enough training samples so that I get uniform convergence, right, that means uniformity for all functions in my concept space, I have that their empirical error is within epsilon of true error, that means then that basically the error rate of the classifier that I output is even 2 epsilon of the best error rate I can hope for a classifier in my concept space. Right, and pictorially it's just this picture here, right? So H star, this is the classifier's smallest error rate. After I see enough examples, its true error rate is even epsilon of its empirical error rate. Similarly for the classifier output by my algorithm, so this is the classifier output by ERM, but I also know that the empirical error rate of the classifier output by my algorithm is smaller than the empirical error rate of the best classifier in the class. So then this picture immediately implies that the error rate of the classifier that I output, the true error rate of the classifier that I output is within 2 epsilon of the error rate of the best classifier in the class, okay, which is great news. Okay, good. All right, and I just want to spend a couple of minutes just to go back, and something that I didn't mention in the class. I just to mention very briefly how we can prove sample complexity statements. I'm going to do the case on H is finite, and how can we prove sample complexity statements in this agnostic case. Actually, it's not very hard. It's, again, union bound plus the right concentration inequality. Okay, cool. So what I want to prove right now is this uniform convergence statement over here, right? So the statement says if I have a class of functions, so the first one, if I have a class of functions that is finite, so if H is finite, then I claim that if the number of samples I see in the training phase is roughly 1 over epsilon squared times log size of H plus log 1 over delta, then with high probability at least 1 minus delta, I have it uniformly for all classifiers in my concept space, their empirical error rate is within epsilon over 2 error rate. Okay, that's what I want to prove. Okay, and the proof is very natural and very simple. Okay, in order to describe the proof, all I need is a concentration, I need a tail bound. Okay, and here it is a tail bound that I need, something called the Hoeffding bound. Okay, so let's think about the following very simple experiment. So imagine that we have a coin of bias P, and imagine that we flip it m times. Okay, now let me think about the number of observed heads. In fact, let me actually think about the fraction of observed heads, right? So let me call denote by n the number of observed heads, and let me think about the random variable, which is the fraction of observed heads. Now, what is the expected value? Okay, it's written over my slide, right? So, but you guys can help me prove it, right? So, what is the expected fraction of observed heads in this experiment? It will be P, right? It's on my slide. Now, can you guys give me a quick argument for that? So the question is, okay, so can you prove to me why the expected fraction of observed heads is P? Or the expected number of observed heads is P times M, right? So in this simple experiment where I flip a coin bias P M times, I want to know what is the expected fraction of observed heads. I claim it's P, but I also want to prove for that. Because it's very simple. There is a key magic word here, or a couple of words. How do you prove it? Linearity of expectation, okay? So basically, I mean, I can just write basically, so the number of observed heads, this is a random variable, I can write it as sum of m random variables, where each xi is an indicator random variable with probability p is 1, with probability 1 minus p is 0, right? The expected value of xi, right, which corresponds to the ith trie, right? The expected value of xi will be p, right? Because it's an indicator random variable. And so then the expected value of the number of observed heads by linearity of expectation will be P times M. I normalize it by M. I give it the expected fraction of observed heads is P. Okay? Cool. So now this is about the expectation, right? So I know that if I flip this coin a number of times, the expected fraction of observed heads is P. Now what tail inequality tells us is how well is this random variable concentrated around its expectation. Okay, so in other words, what's the chance but I deviate from the expectation by more than gamma, say. Okay, and this Hovning inequality shows us that for such random variable, you have exponentially decreasing tails. So right, the specific form of the boundary is written here on the slide. So what we have is that the probability that this random variable, which is a fraction of observed heads, deviates by more than gamma from its expectation p, is upper bounded by e to the minus 2m gamma squared. So you see that actually this exponentially decreases with m, the number of trials. Okay, this is something called Hovning inequality. It's key to learning theory. It's very useful to know. This type of inequality helps us in diagnostic case to prove generalization guarantees. Okay? Cool. So this is the Hovning inequality. And now it turns out that you can easily use this Hovning inequality to then go back and prove our sample complexity result. Right. Oh, I have some typos here. Right. Okay, good. Right. So how do we prove our sample complexity result now, given this tail inequality? Okay. So I claim the proof is very simple. Okay. Given everything you guys know, the proof will be very simple. Okay. So what we're gonna do? What is the bad event that we care about here? The bad event that we care about is that there exists a hypothesis that has the property that its error rate over the sample deviates by more than epsilon than its true error rate. Right. This is the bad event that I care about. Right. And how do I analyze such events typically? Well, I'm going to first fix a hypothesis H, and then analyze what's the chance that something bad happens for that fixed hypothesis H, right? So and then I do union bound, right? That's the typical type of proof in these scenarios, right? So basically, all I have to do here is just apply the tail inequality that I mentioned plus union bound. Okay, and what is P here for me? Okay, when I apply Hovning inequality, what is P for me? P is the true error rate of the hypothesis, right? Because, right, so P is the true error rate of the hypothesis, right? And then I just apply union bound, right? When I just apply Hovning inequality to bound the probability that for this hypothesis, its true error rate is is not within epsilon of its empirical error rate, and from the Hovning inequality, this is exponentially decreasing in m, so it's e to the minus 2m epsilon squared. Okay. So I guess what is the underlying experiment here? If I flip up the coin, like what is the underlying experiment here? So when do I get, I flip, so I draw an example at random, right? If the hypothesis disagrees with the true label, then I make an error. So this corresponds in the Hovning inequality to getting a head, right? That's why it's a direct mapping to the Hovning inequality here. Okay, so I claim, okay, I'm not going to go into many details here, but I claim that if you sit down and think carefully offline, you immediately see a mapping to the Hovning inequality, how we can use Hovning inequality to bound the probability of this bad event happening. So we fix the hypothesis H. What's the probability that H, the error rate of H, true error rate of H deviates by more than epsilon than its error rate? I claim it's exponentially decreasing by Hovning inequality. Then I do union bound over all hypothesis H to give it the probability that there exists a hypothesis H whose true error rate is not within epsilon of its empirical error rate. And we bound that by 2 times size of H times e to the minus 2m epsilon squared, right? Just union bound, and then we set this to delta, and then we just solve. Like as we did in the first lecture, we solve for what value of m ensures that this quantity over here is smaller than delta. Okay, cool. So that's basically the proof. It's not hard once you know Hovning inequality. Right, and then as I mentioned, what this then implies is that if we do so, basically, right, so if we've seen enough examples, right, if we've seen enough examples of it, we then get uniform convergence, then we are guaranteed that the true error rate of the hypothesis output by ERM is only within 2 epsilon of the best error rate we can hope for a hypothesis in our concept space. Okay, cool. So that's the sample complexity for the agnostic case. Right, the key difference with the realizable case is that now it's 1 over epsilon squared as opposed to 1 over epsilon, but we do get something much stronger. So right, now we get uniform convergence. We get that for all hypotheses, good or bad, we get that their empirical error rates are uniform within epsilon of their true error rates. So we get something stronger than what we get for the realizable case. Like in the realizable case, we could only say, well, if you are bad, I'm going to detect you. Right, and now we are arguing good or bad, we will guarantee that your empirical error rate is within epsilon of your true error rate. Okay, so it's something stronger, but we have to pay more. We have to pay quadratically 1 over epsilon. Okay, and this is real. I mean, you can try in practice and see that you're really 1 over epsilon squared here. Okay, cool. So that's one way to state the bound, more in PAC terms, like which says how many samples suffice to get uniform convergence with high probability, so success of ERM, empirical risk minimization. So it's one way to state the bound. And the same way that we did for the realizable case, we can actually derive this bound in a way that gives us a bound for any value of m. No matter how many training samples I have, I can get uniformly for all hypotheses in my hypothesis space an upper bound on their true error rate as a function of their empirical error rate and the complexity of the class, the complexity of the search space. Okay? And notice that really the main difference, again, just to contrast with the realizable case, right? So in the first way of writing the bound, the main difference is in 1 over epsilon now becomes 1 over epsilon squared. In the second way of writing the bound, the main difference is we used to have 1 over m dependence. It was like decreasing linearly 1 over m. Now I have square root of 1 over m dependence. Okay, so this is slow decrease. But because, again, we get something stronger in terms of a guarantee. Okay? Cool. So this is here I have the bounds for the finite hypothesis space case. We can also get absolutely the same type of bounds for the infinite hypothesis spaces by basically just doing Hoeffding instead of everything else. And then the whole machinery that we talked about last time applies. And we get generic bounds that depend on the VC dimension of the concept space. Right? So basically I have here, instead of log of size of h, I'm going to have the VC dimension of h, and similarly here. Okay, cool. So these are the generalization guarantees for the agnostic case, the most general case, as a function of the VC dimension, which has been the classic notion of complexity for more than just 40 years. So, right. So they're nice. These bounds are really nice because, I mean, first of all, they are generic. They hold for any concept class, for any distribution. They can really help you characterize the learnability of any type of supervised classification algorithm you can think about. Okay, so they are super powerful. They hold for any concept class, for any data distribution. And as we discussed last time, they're also, actually in the worst case over the choice of the underlying distribution, they're also nearly tight, up to some pesky log factors. Okay, they're nearly tight in the worst case of the choice of the distribution. Okay, so they have very nice properties. However, they also have a couple of drawbacks. Okay, so here are the drawbacks. The first drawback is, I mean, while they are nearly tight in the worst case over the distribution, they could be extremely loose when the underlying data distribution is nice, right? If the distribution is more benign than the worst case, they can be extremely loose. So last time when I mentioned the lower bound, if you guys remember, the lower bound holds for a very skewed distribution, right? And don't expect most real-world distributions to be so nasty. Okay, so for nice distributions, these bounds might be very loose. Okay, so that's a bit unsatisfactory. So that's one drawback. And the second drawback, and this is the most significant one actually, is that these bounds only hold, right? The VC dimension notion itself only makes sense for binary classification. But as Tom mentioned many times, in machine learning we care about many other types of function approximations more generally, like regression or multi-class classification and so on, right? So it would be nice to have a general machinery that can help us analyze the learnability of these more general function approximation types of problems. Okay, and it turns out that luckily that's possible in a very, I think, reasonably clean way by using something called Rademacher complexity bounds. Okay, and I'm going to try to go through this in the next 10, 15 minutes. Okay, I'm not going to attempt any proof. I'm just going to try to give you the intuition behind the concept again. And I guess I just want to mention that actually that's kind of cool to teach this in this class because these are very modern bounds. So while the VC bounds have been around from, I know, for more than 40 years, these bounds really just became popular, or like people realized that they are the right notion of bounds for general function approximation problems when I started my PhD. So that's pretty cool, 10 years ago. Okay, so after my lecture today, you'll know lots of modern stuff about machine learning. And moreover, you also know if you have any function approximation problem, how to think about analyzing the learnability of your algorithm, which is super important, right? We also want to be able to analyze how much data do we need for our algorithms to do well. Okay, and these are very generic bounds that will help you to think about many classes of problems. Okay, cool. So just a couple, just to read out from the slide, a couple of very good properties of these bounds. So number one, as you'll see, there are data-dependent bounds, that sample-dependent, and in fact, they are distribution-dependent, and in fact, sample-dependent bounds. So if your data happens to be nice, the bound will capture that. That's number one. Number two, they apply to general classes of real value functions. So to general function approximation problems, and they can be used to recover the VC bounds for supervised classification. Okay, so which is good. And also, they have been the prominent technique for generalization bounds in the last decade. Okay, and actually, this is a nice survey that encapsulates these bounds, but really most of the modern books on foundations of machine learning start with these bounds, so they use these bounds. So something definitely that you want to know. Okay, great. So any questions before I go on? Okay, so as you see, actually, they have lots of nice properties, but they do have a tiny bit of a drawback. They are not as clean as a VC dimension-based bound, right? So VC dimension-based bounds are so nice that Sota could tell me the definition right away, and she remembered everything, right? These bounds, they have all these positives, but they will have, they're not, at the basic level, they're very intuitive, but at an operational level, you still have to do a bit more work, okay? So let me mention what they are. Okay, and because these bounds are so general, I need to present them in a more general scenario, right? I need to abstract out a little bit the whole setup. Okay, so let me mention the setup in which we're writing the bounds, and then I'm going to mention how binary classification is a special case of that. Okay, so now what we're going to think about is, imagine that you have a space Z, right? And let's imagine that you have a class of functions from Z to the interval 0, 1. So that's bound in interval 0, 1. Now let's also imagine that you have a distribution over this space Z. And let's imagine that we've seen a random sample drawn IID from this distribution. So we have a sample S given by Z1, Z2, Zm. All these Zi are drawn independently and identically distributed at random from the underlying distribution D over this space Z. Now, the kind of question that these bounds help me understand is a uniform convergence type of question, which in this more generic framework just means what I want is to write a bound that is a uniform convergence bound, bounding uniformly for all functions in this space of functions F, the expected value of the function F on a point drawn at random from the distribution to the empirical average of the function F over the sample S. Okay? And I want to bound this as a function of the niceness of the class of functions F and niceness of the distribution D, or even of the sample S. Okay, so this is a type of bound that we think about in this, when we write down the macro complexity bounds. Okay, now just to quickly mention how is this related to the type of bounds we've been talking about, how is this related to binary classification? Well, in the binary classification case, then Z for us will be the product between the instance space and the label space. Now, given a class of classifiers, which could be linear separators or decision trees and so on, so given a class of classifiers H, I can think about the class of functions F, which is just the class of loss functions induced by my classifiers. The class of loss functions induced by the classifiers and the 0, 1 loss. Okay, so for every function, for every classifier H, I can just associate a loss function, which now takes in a pair XY, so that's a point Z, and it outputs 1 if the classifiers agree with the label of X. The classifier, the label of X given by the classifiers agrees with Y, the true label, and 0 otherwise. I mean, so really this is just the loss function, the class of loss functions induced by my classifiers and 0, 1 loss. And I claim that if you just think about it, then you'll immediately realize that the expected loss, so for such a loss function, the expected value of the loss on a point drawn at random from the distribution D is exactly the error rate of the classifier. Okay, and similarly for the empirical loss, for the sample loss. Okay, so basically, which then immediately would translate, this type of complex system, then it would immediately translate into a bound on the generalization error for my classifier. So uniform convergence bound on the generalization error of my classifiers. Okay, cool. So I'm just arguing that the binary classification case that we've been talking about is a special case of this more general way of phrasing the problem, But why do I care about this more general way? Because then I can use it for regression. I can use it for multi-class classification. So for example, here, instead of having y to be minus 1, 1, I can have a general discrete y. I can have a general discrete output space. Instead of having here the 0 and loss, I could have the square loss, right? So basically, if I write the bounds more generally, then I can instantiate for my them for my specific problem. Okay, so for these reasons, what I want to do right now is to basically think about this more general setup. So that I described over here, where I have a space z, I have a class of functions from z to the interval 0, 1, so bounded interval 0, 1. I have a distribution d over z, and what I care about is getting a uniform convergence bound, bounding uniformly for any function f, the expected value of f on a sample drawn at random from z with its empirical average over the sample. And plus, and as a function also of a complexity term that depends on the niceness of f and of the sample. Okay, so let's think about that more general setup. Okay, and for this general setup, there is this very interesting notion called Rademacher complexity that gives us bounds, but to help us give uniform convergence bounds based on this Rademacher complexity f. Okay, and before even I go through the notation on the slide, I just want to mention that basically at the most basic level, what this Rademacher complexity measure is capturing is how well can I fit random signs, random labelings with functions on my concept space. That's all it measures. I mean, you think that if I can fit random labelings very easily, that means my class is very big. I cannot hope to achieve any uniform convergence guarantees. I cannot hope to achieve any learnability guarantees, right? If it can fit any random labeling, right? On the other hand, if the ability to fit random noise is small, that means that I can have a small capacity, so that means I can hope to achieve uniform convergence guarantees. Okay, so that's all Rademacher complexity measures. Okay, and let me go slowly through it now. Okay. Cool. So again, we have a space Z, we have a distribution D over Z, we have a class of functions from the space Z to the interval 0, 1. And let's imagine that we have drawn a sample S from this distribution Z. So we have a sample of points Z1, Z2, Zm that are drawn IID from the fixed underlying distribution over the space Z. Okay? And let's imagine doing the following. So what I'm going to do, in order to define the Rademacher complexity, I'm going to, for each sample Zi, I'm going to draw a Rademacher variable sigma I. So for sample Z1, so what is a Rademacher variable? Rademacher variable is just a very simple variable that is just uniform over the set minus 1, 1. So if probability a half is minus 1, with probability a half is 1. That's what the Rademacher variable is. And so what I'm going to do for each sample, right? So I fix my sample S, and I'm going to define something called the empiric Rademacher complexity. What I'm going to do is for each Zi, I'm going to draw a Rademacher variable sigma I. So for Z1, I'm going to have sigma 1. For Z2, I'm going to have sigma 2, and so on. For Zm, I'm going to have sigma m. Okay? And then what I'm going to do, I'm going to look for all functions in my concept space, and I'm going to try to see how well can I fit these random signs with functions from my concept space. So I'm going to go ahead and look for all functions in concept space. I'm going to try to correlate as well as I can these random signs sigma 1, sigma 2, sigma n with the value of the function. Okay? And then I'm going to repeat this a few times, and I'm going to take the expectation. Okay? So to go again slowly, what soup inside this soup here measures is for a given vector of Rademacher variables, which are just random labelings, for a given vector of Rademacher variables, how well can I correlate my vector of Rademacher variables with functions from my concept space? Okay? And then if I take the expectation over these Rademacher variables, then this just measures the ability of the class F to fit random noise. Okay? It's very, very intuitive. Super intuitive, right? Basically, all I do is just measure the ability of the class of functions F to fit random noise. Okay, let's take a, and then, okay, I just want to mention that, okay, now once you have this definition, so this is the empiric Rademacher complexity. I can also then take expectation over the sample S, and then I get something called the Rademacher complexity. Right? Notice that this depends on M. So this notion, both the empirical Rademacher complexity, so the empirical Rademacher complexity depends on the sample itself, and also on M implicitly. Right? If I take an expectation over the samples, I get something called Rademacher complexity, but that depends on M at level M. Okay, but for simplicity, let's just think about the empirical Rademacher complexity for the lecture today. So all I want to think about is this empirical Rademacher complexity. Right? This quantity over here. Good, and it turns out, and let me mention, okay, and we'll come back to it and do a couple of examples, but let me just mention that it turns out that we can now write very generic sample complexity statements that just involve as a complexity measure this Rademacher term, Rademacher complexity term. Right, so what we're going to be able to say is that uniformly for all functions in the concepts, for all functions in my set of functions f, I have the expected value of the function on a point drawn from the distribution is upper bounded by the empirical value of the function plus the Rademacher complexity term. Okay, plus some small term. This is, I'm thinking about it as being very small. Square root of 1 over m, it's super small. Okay, so we can even ignore this one. So this, we can just ignore them. So we just, and let's actually just focus on this one because it's the most important for the class today. Right, and so basically what we get, a uniform convergence statement that upper bounds the true expectation of f by its empirical expectation plus this Rademacher term. Right, and this holds uniformly for all the functions in the function space and for all values of m. Now, obviously, for this bound to be meaningful, I mean, typically we think if we increase the number of samples, we want to do better and better, right? That's a typical way of thinking, right? And so for this bound to be helpful, what we want is that this term, this Rademacher complexity term, decreases with m, right? If it stays constant, then it's no good. You know, you're just telling me something meaningless, right? I mean, because these functions, recall, these functions f are bounded in the interval 0, 1. Right, so if this would be a constant like a half, then that's not very helpful. You're not getting the expected value of the function close to its empirical value. Yeah? So we really want to think about cases where this decays with m. Yes?
Can we say this Rademacher complexity is between -1 and 1 for this case always?
Yes, that's an excellent question. Let's see how big it can be. So it's between -1 and 1, right? Because each term here, right? So that's perfect. Actually, excellent point, right? So this is like, let me write this down. That's an excellent point. So you are Mustafa? Okay, good. So Mustafa says, so that this is all obviously between -1 and 1, right? Just because we average numbers that are between -1 and 1, right? Yes, we can even put it between 0 and 1 because the soup, I mean, you can always, yeah, okay, by -1 and 1 is a legal bound. Okay, absolutely. Okay, let's think about it that way. Okay, good. All right, and let's do a couple of examples, okay? Because we need to, I mean, so basically at the basic intuition level, this is clear, right? What we think is if f is very large, contains many, many functions, we'll expect this quantity to be very, very large because it means we're going to be able to fit random signs pretty well, right? We expect this. On the other hand, if f is very small, we expect this quantity to be much smaller, okay? So intuitively speaking, it's very clear what's going on. Let's go and do a couple of examples just to get a bit more intuition. Okay, so here's a question for you guys. Let's think about the simplest case. When f, the class of functions, just contains one function. Okay? Then I claim that the empirical Rademacher complexity is exactly 0. So do you guys see why? It's not very hard. Let's think about it. So any thoughts? I'm just saying, let's think about the case where the class of functions f contains just one function. It's just an arbitrary function from z to 0, 1. It's just one function, right? I mean, let's think through it. So what happens in that case? This soup goes away, right? Because there is no soup to, I mean, like it's just one function, right? I mean, I just only have one function left. I mean, one function, okay? So then what is the expected value, right? So then what is the quick argument that I already wrote it here, right? I then claim that the expected value over these random signs of sum of sigma I f of zi is 0. I wrote it down. Why?
I think the expected value of sigma will be 0. It's between a uniform distribution -1 and 1.
Yeah.
The expected value of that will be 0.
Yes.
And f is just a constant number, so it really doesn't matter. I mean, that is the only part that matters over there.
Right. Exactly, right? So Mustafa is giving us the argument. So basically, because then I only have one function left, because, sorry, I have only one function in my class, when I just have the expected value over this sigma 1, sigma m, of this quantity, sum 1 over m, sum of sigma I, f of the I. And as Mustafa noticed, the expected value of sigma I for each I is 0, because it's plus minus 1 with equal probability, right? And then if I take linearity of expectation, then I get 0, right? Because the expected value of sigma f of the I for all I is 0, so then by linearity of expectation, this is 0. Okay, so very simple. So if the class of functions contains just one function, then I claim that the Rademacher complexity is exactly 0. Empirical Rademacher complexity is 0. Right? So which is kind of interesting, because if I go back to my bound here, that means if I contain only one function, then I only need kind of, so this will go away. So I only need roughly 1 over epsilon square samples to get this expectation, true expectation of epsilon of the empirical expectation. So this is what to actually expect from the Hovding bounds themselves. Okay, so that's good. Okay, now let's do another case, and then I'm going to ask you guys, so what happens if f contains all the functions in the interval 0, 1? What is the empirical Rademacher complexity? So that's the other extreme case, right? We did the first simple case. How about the other extreme case? When f contains all the functions in the interval 0, 1. So here you have a lot of freedom, right? When I do the soup, right, for every instantiation of random labelings, right? I mean, if I pick, for example, I can pick here to be 1, minus 1, oops, 1. I don't know what's going on here. Right, anyway, for every instantiation of random labelings, oh no, I don't want to give this away. Pen. Okay, so right, for every instantiation of random labeling, so here are my Rademacher variables. Right, I can have a freedom, right? I have all the functions in the class, and I have freedom to pick a good function to help me correlate as well as I can with the random labeling, right? So then what is the empirical Rademacher complexity then? Somebody, we'll see. Right, so sigma i's, these are between either minus 1 or 1, yeah? And the functions are between 0 and 1. Right, obviously, if I get a 1, right, if sigma I is a 1, then I want to pick a function that gives me 1 of that sigma I, right, to make it as large as possible. If I get a minus 1, like if sigma I is minus 1, I want a function that would give me what? The functions are between 0 and 1. I want the function that gives me 0, right? Right? Because this is when I maximize. I mean, if I contain all the functions in the class, I kind of do independent decisions for each sigma I, right? If I contain all the functions, right? If my set of functions f contains all the functions in the interval, okay, so I should have this, right? If f contains all the 0, 1 functions, that means basically I can do an independent decision here, right? And so if sigma I shows up 1, then I'm going to pick a function that on zi says 1. If sigma I shows up 0, if sigma I shows up minus 1, I'm going to pick a function that on zi says 0, because then I just sum everything up. This is when I get the maximum correlation, right? If I do so, then what is this expectation? Then what is the empirical Rademacher complexity if I do so? Right? If it would be the yeah? It's not quite 1, right? Because what happens if sigma I shows up 1, right? Because these are minus 1, 1 random labelings, right? As I said, the way to maximize it, if sigma I shows up 1, right? So if sigma I, so here is here of my vector sigma. If sigma I shows up, pick a function that says 1 there, right? If on the other hand, if sigma I shows up minus 1, like this one here, because I want to maximize everything, I'm going to pick a function that says 0, right? So then basically really the expected value, right, over sigma here will be really when I get the expected number of 1s in my vector sigma, right? But what is that? The expected number of 1 in my vector sigma. Half of the times, exactly. So that's m over 2, right? Then I get, right, half of the time m over 2 over m, so then I get the empirical Rademacher complexity is a half. Okay? Which is good, right? I mean, because we don't expect to, why is good? Because it's a constant, and if we contain all the functions, we don't expect any uniform convergence, any reliability guarantees, right? So that's great, because if I go back to my bound here, as I said, if the bound remains a constant, oops, okay, maybe I should go forward. Right, so if I go back to my bound here, right, if the bound If this remains a constant, then I don't get any implications about generalization abilities here, right? Okay, cool. So we have two extremes. So now I understand that this Rademacher complexity means on two extremes. So the one extreme is when the class of functions only contains one function, and when the empirical Rademacher complexity is 0. The other extreme when the class of functions contains all the functions, and the empirical Rademacher complexity is a constant, which is good because then we don't expect any generalization abilities. Okay, cool. And then, of course, we can think about in-between cases. We can then, for example, think about what if f is a class of loss functions induced by binary classifiers, which is what I've been talking about so far. Now, it turns out that then you can actually do some, it's not hard, but I'm not going to go through it because it requires doing hoping and union bound. You can do an argument, a probabilistic argument, and then argue that in that case, the empirical Rademacher complexity is upper bounded by, when the case on H is finite, is upper bounded by square root of log size of H over M. Okay, and this is when H is finite, and when H is not finite, then we get the empirical Rademacher complexity is upper bounded as a function of the shattering coefficient that we've been talking about last time. Okay, and it turns out that actually we can then use this to recover the typical VC dimension-based bound. Okay, so it all relates together at the end of the day. Okay, and this statement here is not obvious. If you're curious, come and talk to me about it. It's not hard either, but I don't have time to go through the lecture right now. Okay, cool. So basically, just to summarize this discussion about Rademacher complexity, so this is a very intuitive notion of complexity of a class of functions. It measures the ability of the class of functions to fit random noise. Okay, so you would expect that if that's very high, then we shouldn't be able to get generalization abilities, and this is exactly what the bound written here captures. Okay, and the nice thing about this bound is that it's a data-dependent bound. So it depends on the underlying distribution, depends on the sample. If my distribution is nice, because this depends on the underlying sample and the underlying distribution, this bound could be very, very tight, as opposed to VC bounds, which are worst case type of bounds. Okay, and I didn't go actually through the proof here, but I can tell you that actually it's very, very interesting. Technically here, actually the proof uses the exact same tricks that I mentioned for the VC dimension-based proof. We use a ghost sample and the symmetrization trick. Okay, so again, it all connects together in a nice way. Great, and as I already mentioned, actually in the case when f is a class of loss functions induced by binary classifiers, we recover the VC dimension-based bounds. And so here are these bounds, both the VC dimension-based bounds and the Rademacher bounds written down for the binary classification case, where we have a class of classifiers like linear separators, decision trees, and so on. And then we can write these bounds that relate uniformly for all the functions in my concept space, where through generalization error, where empirical error as a function of the complexity of the class. For VC bounds, this is distribution independent. For Rademacher-based bounds, this is distribution, in fact, data dependent. So this bound could be much tighter. Okay, but the cool aspect about these Rademacher complexity bounds, in addition to the fact that they are data dependent, actually they are very, very general. So you can use this thinking to derive bounds for regression, for multi-class classification, really for any function approximation. Okay, so all you have to do in a specific case to compute the empirical Rademacher complexity. And there is a whole machinery. People have come up with all sorts of tricks, for, like all sorts of composition results that will help us to do this job for the specific problem. Okay, and actually some of the techniques that we're going to talk about later in the course, like SVM, boosting, and so on, we can derive bounds for those techniques, again, using Rademacher complexity. So it's a very general, very, very useful tool. It's the right way to derive sample complexity statements or generalization guarantees today. And it's also very intuitive. Great. Okay, so now in the last few minutes, I also want to talk about, so I want to go back to some of the questions that I got last time. So I guess Sweta was asking me last time, how can you use these bounds? I mean, so the way I describe the bounds so far is really, as I mentioned, there are two purposes, two uses of the bounds. One of them is just for getting understanding, right? Like a first cut understanding. So for example, we can use, say, the VC dimension-based bounds to know that, for example, the VC dimension of the class of linear separators is D. So then we know how many training samples we need, in principle, to learn if the target function is close to being a linear separator. And how is it scaling up with the number of features, right? So we can just use the bounds to really get an understanding of, in principle, how many samples do we need to learn well. Yeah, that's one use of the bounds. And it's actually one of the most common uses. one use. But what I was asking, can I also use the bound to design a better algorithm? Okay, and this is what I want to talk a little bit about now. Okay, cool. So I guess any questions before I go on about the concept I've been talking about so far? Comments? Okay, so when no questions or comments, then I'll ask you a question. Good. So, okay, so let's look at this bound over here, right? So let's just pick up, this is the this is the Rademacher complexity bound for classification, and this is the VC bound for classification for the agnostic case, really, right? So why is this a bound for the agnostic case? Can you quickly tell me? So in the agnostic case, what is the dependence on M that I should have? What is the right dependence on M that I should have? Square root of 1 over M, right? So in the agnostic case, what I need to see is square root of 1 over M here, right? In the realizable case, I could have 1 over M, so better dependence on M, right? So this is the bound. When you see square root of 1 over M, you should immediately think that's the agnostic case, the most general case. Okay? Good. So let's just look at this bound, for example, here for the VC bound for the agnostic case. Okay, and we can immediately notice that, so far we thought about the class H as being fixed, right? So we thought about the class H as being fixed throughout our discussion. Okay, but let's now change a little bit the question. Let's think about the case where we have a fixed set of training samples, and we are thinking about doing model selection. Which class of functions should we use, right? And we know based on these bounds, right, that basically I'm just writing this a simpler form here. So we have what these bounds tell us for a fixed class of functions H, uniformly I have for all functions in the class, the generalization error is represented by the empirical error plus some complexity term, right? And so now if I have a fixed set of training samples M, and I'm trying to do model selection, right? You might wonder what class of function should I use? Linear separators, decision surface of degree 2, 3, and so on, right? What should I be using? Now, obviously, right, okay, so what happens if I increase the complexity of the class of functions? So there are two terms that I have to think about, right? The empirical error rate and the complexity term, right? Now, let's think about this, let's think about it pictorially. So what happens if I increase the complexity term? So what happens if I increase the complexity of the class of functions? What happens if I start using more and more complex classifiers? What happens with the first term, the empirical error rate? If I allow you to use more and more complex classifier? Yeah? Yeah, so if I increase the complexity of the class of classifiers, like as I keep increasing the complexity, I'm going to be able to fit the data better and better, so the training error is going to go down. That's my red curve, right? But on the other hand, as I increase the complexity, right, so initially at low complexity, especially if M is sufficiently large, initially low complexity, the generalization error stays close to the training error, but at some point I'm going to start overfitting, right? Because this second term over here, the complexity term, is going to start dominating, right? So then the generalization error will go down and then up, yes? No. So that's a fixed M, and I'll come back to your question. Okay, so let's think about fixing M, the number of training samples, and let's think about what you would expect to happen, right? If I fix M, if I increase the complexity of the class of functions, then obviously the training error is going to go down, right? Because I can fit better and better. Now, what happens with the generalization error? Well, I claim we're going to initially, very low complexity of the class of classifiers, they're going to stay close to each other, but at some point, because of this second term, we're going to go up, because the second term is going to start to dominate, so then this is exactly when I get overfitting. And this is fixed term. And I'll come back to your question. You asked a great question last time, okay? But I'll come back to it in a couple of slides, okay? So this is what we expect. Now, the question is, okay, so what this obviously shows that it's not a good idea to just do ERM, right? It's not just a good idea to just, find the classifier of the smallest empirical error rate in all possible classes, because, obviously this shows it's not a good idea, right? But the question is, can you use the bound to do model selection? So can you use the bound to somehow get a classifier whose error rate is close to the bottom of the blue curve, right? Because that's the best we can hope to achieve, right? And the answer is yes, and that's why we have this amazing machinery that will give us, will help us answer that question, yeah? So the answer is yes. So okay, I'm going to add to my picture another curve, which is the upper bound on the true error, right? So we have an upper bound on the true error given by the generalization bound, the empirical error plus some complexity term, and without sample complexity guarantees tell us that with high probability, the generalization error, the blue curve, will stay below the black curve, right? Probably. right? And so what this then suggests, what we want to do is to basically minimize the upper bound on the generalization error. So we want to minimize, to find the minimum of the black curve, right? And if we do so, if our bounds are good, which they are, right? If we do so, if the bounds are good, then we know that basically the bottom of the black curve will be close to the bottom of the blue curve, right? And then we kind of get the best we can hope given the amount of data that we have. The best we can hope given the evidence that we have. So if we minimize, instead of minimizing the error rate, we're going to minimize the error rate plus the penalty that has to do with how complex the function is, right? We know that we're going to get a classifier whose error rate is very close to the best we can hope for, which is the bottom of the blue curve. Okay, so this is pictorially the principle, the empirical, the structuralism minimization principle. This is the SRM principle pictorially. Okay, and then we can just write down some math, okay, which I'm actually not going to go through. Okay, you can just write down some math and then argue that, yes, indeed, because the bounds are good, I'm going to get at the bottom of the blue curve is close to the bottom of the black curve, so I'm doing great. I can get the best I can hope given the amount of data. Okay, cool, but I want to go back. What's your name? Karen. I want to go back to Karen. Karen had a great question last time, so he had a very nice question. So when I did this picture, I fixed M, the number of samples, right? Because I wanted to think cleanly. Now what happens if I increase M? What do you expect? How do you expect the picture to change? Yeah? To move to the right, right? So basically these two curves will stay close together for longer because I have more samples, and basically this kind of the bottom, this bottom of this blue and black curve will move a little bit to the right. Yeah? Great. Cool, so as you can see, we can also use these bounds to actually do model selection, yeah, which is one of the hardest questions in machine learning. So it's nice that we can now use these, these fundamental principles to kind of try to attack the question of what's the best I can do given the amount of data that I have. Yes?
So if the number of samples we take is infinite, will the true error and staging error converge, be equal at some point?
Yeah, if the class is also have finite complexity, yes. Yeah, I mean, if the class is also infinite complexity, when things become more subtle, it's even hard to think about what happens. But if it has finite complexity, yes. Yeah. What's your name? Druvin. Okay, cool. Great. So, okay, that's SRM. We answered the question, what happens if we increase M, which is current question last time. Okay, let's see what else I want to mention today. So I'm going to skip the math. You have it on the slides. You can look for it offline. Oh, yeah, I just want to mention just a couple of remarks, and then Tom will going to continue. So just, right, we see that basically, in order to handle overfitting, so we can use these fundamental principles like generalization bounds to do structures minimization. We can probably, if we ignore computational considerations, that's probably the best we can hope for. Now, as we know, in machine learning, sometimes there are computational barriers in the worst case. So it turns out that actually really doing this minimization problem, finding the classifier that minimizes the empirical error plus some penalty that depends on how complex the class is, that's typically very hard computationally. It's MP hard, I mean, if not much harder. Okay, so it's really hard. So it's often computationally hard. There are some, but actually there are some nice cases. Actually, I found this very nice paper by two of my favorite learning theorists. So it turns out that there are some nice cases that actually can do that. And one nice case is connects to the very first lecture, so connects back to decision trees. So if we manage to use ID-free algorithm to find basically a tree that is perfectly consistent with the data, then it turns out that we can use this generalization bound to do pruning and to kind of get the best we can achieve given the amount of data. Okay, so sometimes there is a very nice example actually where you can use SRM and you can implement precisely the structures minimization principle in a computational efficient manner by using dynamic programming to do decision tree pruning. Okay, it's kind of interesting. And if you like algorithms, it's a neat thing to think about. Okay, so often it's hard. So doing structures minimization, really minimizing or the bound, or minimizing the upper bound on the generalization error, doing this SRM is typically hard, but there are some very nice cases where we can still do it. Okay, cool. Now let me also mention just that also there is a very related family of algorithms that is very, very much similar in spirit to structure minimization, and this is called regularization. So these are regularization-based algorithms. where basically, again, just minimize something that looks very, very similar. So minimize the empirical error rate plus typically would be some lambda term times the norm of H in some vector space. So we need to have a vector space and to have to think about the norm of our classifier in that vector space. Like linear separators, for example, and can do an L2 regularization by using an L2 norm there. Or I can use a general LP norm. I can use maybe an L1 norm there, or and so on, right? So there is this whole family of algorithms called regularization-based algorithms, but conceptually speaking, they are very, very similar to the structural minimization type of algorithms, right? They minimize empirical error rate plus some penalty term. Here, the penalty term has a very specific form. It's just the norm in some vector space. Okay? So, and actually, many of these algorithms can be analyzed through the length of structural minimization. And people have done that in the literature. Okay, so formally you can provide guarantees on their generalization abilities by using principles of the type that I talked about. Okay, and I guess another technique is also cross-validation, right? So here we are trying, in SRM and the regularization, we are trying to use the data the best possible, to use the amount of data in the best possible way we can. I guess another related technique it's widely used in empirical machine learning is to do cross-validation, or use a holdout set, right? And so just pick the classifier that does the best on, say, the holdout set. That's the simplest form of cross-validation. Okay? And even for this class of families, one can prove guarantees about when do they do well. Okay, so these are all techniques for handling overfitting, and I guess the nice thing, because we are finishing here the learning theory part of the course on generalization bound, the nice thing is that we can analyze all these formally by using all the tools that we talked about. So the deep tools that we talked about will help us be confident that these algorithms are doing the right thing, and they're using the data in the best possible ways. So it's really important to be able to analyze sample complexity guarantees. Cool? So any questions? Okay, so let me just summarize. Tom, you'll talk for 10 minutes, right? Mm-hmm. Good. Okay, so just to summarize what we've been talking about so far, so in this module of the course, we'll be talking about sample complexity or generalization guarantees. And we've been looking first at the case where we're just trying to get sample complexity guarantees for supervised learning, binary classification. It was the easiest case to think about, where we're able to go in detail through sample complexity bounds, like when H is finite, we're able to come up with a formal proof, one slide proof of how many samples we need in order to learn well. And I definitely expect you to know that. Actually, I'm going to put it in the exam as a question. I'm announcing it up front. You will be asked in the exam to prove a statement. Okay? So to make sure that you guys understand it, I'll announce it up front. Good. You can get 3 points if you understand it, which is great. Good. So we've seen this basic sample complexity statements on H is finite, and then we've seen like a much more advanced machinery for analyzing sample complexity statements on H is not finite using scattering, BC dimension, and so on. And we discussed basic, very classic bounds from the 70s based on VC dimension, upper and lower bounds. And this was last time, and today we talked about an even more modern and more advanced machinery, much more general, based on Rademacher complexity. And we also talked about model selection and structures minimization. Okay, so these are all concepts you guys should be very happy with, I guess. Yeah, should be very familiar with and understand them deeply. Okay, because then that can help you understand, I think, a lot of the essence of machine learning. Cool. So I guess if there are no more questions, I'll let Tom go on.
Yeah, let me take 5 minutes. Can we go there? So one way to think about what Nina's been talking about here is she's really telling us the theory that underlies overfitting. It's really, that's what all these results are about, right? If you look at this expression, she's asking, what's going to be the difference between the error that we see for some hypothesis over a sample of data that we trained on, that we're using for training, versus the error of that hypothesis under the whole true distribution D that's generating that sample and other data that we're going to have to deal with in the future. Right? And we care a lot about overfitting. We don't like overfitting. We like our estimate of the, that when we optimize the, by picking a hypothesis that works very well on the training set, we want it to be also very good on in the future, on the true data. And so really, she's been telling us an underlying theory that tells us how bad can the difference between these two things be? Right? And that's what this Rademacher complexity is telling us. That's what the VC dimension is telling us. And both of those measures are really general measures over the hypothesis space, the set of hypotheses we're going to consider. And then this idea of structural risk minimization is really very interesting. We could ground this, for example, by saying H1 is the set of all decision trees of depth 1. H2 is the set of all decision trees of depth up to 2, 1 or 2. H3 is the set of all decision trees of depth up to 3. And if we compute the complexity of those different sets that I just mentioned, then this is going to tell us, given the amount of data, the M, the number of examples that we have, what's our best bet in terms of how complex a decision tree should we try to learn? And to do it in a computationally efficient manner. Good point. Right. So I just want to add one slide to what we've been thinking about, or one idea, which is, well, if this is one way to look at how to avoid overfitting, and in this case, structural risk minimization tells us, well, then go with this hypothesis space instead of this one. Use H3 in this case because M, the number of examples you have available, is this. But if you think about it, we've already seen another way of dealing with overfitting, which is regularization. And regularization is kind of, it's interesting to think about these two next to each other, because structural risk minimization, it tells us which class of hypotheses to consider. But it doesn't tell us how to resolve within that hypothesis class which one we want to choose. It just says, yeah, use the set of all decision trees of depth 2 or all decision trees of depth 3, if I say it that way. But it just says use that hypothesis space, and then go ahead and pick the best hypothesis you can find in that space. But regularization is kind of a finer tuned notion of preference over hypotheses, because regularization tells us not just which class of hypotheses to choose, but within that hypothesis class, which one to choose. And so I want to add one slide to today's presentation. I'm going to keep your annotations. I'm going to try to leave PowerPoint. Won't be easy. Okay, I'm saving your results. Okay, good. And I'm going to try to pull up one slide. Which is here. So let me I just want to start the slideshow. I don't want to do anything tricky. Let's do that. We can come back and talk about this other stuff another time, but let's remember what regularization was. Regularization, when we talked about, for example, logistic regression or linear regression, where we were trying to learn some function that, let's just think in terms of, we're trying to learn some function, oh no. I'm not even gonna, oh. We're trying to learn some function, I'm not even gonna do that. We tried to learn some function that's going from x to y, and we're learning those weights, remember the little w sub i's, either for logistic regression or for linear regression. And then we talked about the fact that we could do maximum likelihood estimates or map estimates. That vocabulary that I was using, saying that we could use maximum likelihood or map estimates, was kind of the statistician's vocabulary for talking about regularization. So when we talked about doing a map estimate, which is right there at the top of the screen, we said we want to choose the set of weights that will maximize the log of the prior on our weights plus the log of the data likelihood. That was the vocabulary we were talking about, because that, by Bayes' rule, would also maximize the probability of W given the data, given the x's and the y's, and our priors. So we said we wanted to do that, and then we said, well, what if we make up a Gaussian prior on our weights? Then it turns out the log of that Gaussian prior, when we want to use it in that top expression, just turns out to be the sum over all the weights of the square of their magnitude. So that prior is, if we think of suppose I only have two weights, then that prior is a kind of Gaussian centered where all the weights are 0, and then it goes down as the weights get bigger and bigger. And then we said, well, okay, if we want to maximize that product, or the log of the product being the sum of the logs, then we could think of there's some probability of the data given the weights. There's also some prior W, and if we want to maximize the product of those or the sum of their logs, then we have to take both of these things into account. And by the way, it turns out that if you think about it, where these things, if I drew for all possible weights the probability of the data given particular choice of weights, I'll get some contour here. And it turns out that if I want to maximize that quantity, the maximum is going to be where the contours for this thing are tangent to the contours for this, touch the contours for this thing. One way to notice that is, suppose this is a point we're considering as a possible maximum for those. Well, if I move away from this, I'm moving, if I move tangent to this, I'm moving downhill in both of those. Okay, so this is sort of where the ridge of the maximum is. And so you can think of this regularization as just a way of saying I have a very smooth prior over my hypotheses. And then given the data, I'm going to pick the one whose posterior probability is maximum. And so if we make up, for example, a Gaussian prior on those weights, that gives us this kind of expression to add in, and it gives us this kind of diagram. And I drew that as a spherical Gaussian. There's another type of regularization that's very popular. In fact, these are the two types of regularization that are most widely used in practice. This one comes if instead we make up a prior which is called the Laplacian prior. Here I've plotted both the Gaussian one and the Laplacian one. Laplacian prior is much more peaked. I made the mean of both of those 0. But if we use the Laplace prior, then the first, the log of that turns into this form instead of this form. So it's not the square of the magnitudes, but just the magnitudes. And so, you know, that gives us this kind of a form for the contour of equal probability weights, right? This is linear because, you know, I could trade off, if I subtract delta from W1 and add it to W2, I'll have the same sum of the magnitudes. So, so this is another one of these pictures I carry around in my head. It's actually a double picture. And the reason I carry this around is that it reveals a very fundamentally interesting truth about L1 and L2 regularization. The truth is that for L1 regularization, many of the points that are optimum end up with 0 values for many of the weights. So if you think about it, if I have this kind of surface, of this kind of contour of equal probability on my prior, instead of this kind of contour, it's much more likely that the points where we optimize the sum of these things will be along a point where at least one, or in fact in multiple dimensions, many of the weights have the value 0. And so these two ways of doing regularization are both very popular. If in many cases, the reason people use L1 regularization is if they're in a situation where they think, well, I have 1 million x sub i's, and I don't think they're all relevant, but I'm afraid of throwing them away. So I'll just include 1 million x sub i's, but I'll use L1 regularization. And it turns out that is a way of putting in a prior that effectively says, I believe a priori that most of these x sub i's should have a weight of 0. They're mostly irrelevant, but not all of them, and I don't know which ones. And so L1 regularization gives you that property, whereas L2 doesn't really. It's, of course, encourages all weights to be close to 0, but not in this kind of different way where this forces many weights to be exactly 0. This one just encourages all of them to be close to 0. So think about that, and we'll see examples of L1 and L2 regularization as we go through the course. But I think the 2 points here are L1 and L2 are the 2 main kinds of regularization. But also think about the last couple lectures, what we've been talking about. It's really been a theoretical discussion of the relationship between how complex a set of hypotheses should we consider, given amount of data that we have, in order to achieve with some probability over the training sets that we might actually see, that will achieve a certain bound on the overfitting, the difference between observed error and the true future error. And this regularization is just another way, but more out of the culture of statistics for trying to get at the same kind of things.
But we can use boundary type I talked about to actually analyze this format.
That's right. So we can bring those two together, but let's not do it today. Thanks. So next time, by the way, we're going to launch into a multi-lecture series on graphical models and Bayes nets. So